If it's a value this large for K, then it's going to happen at a fast rate. We consider that fast. If it is at order of magnitude of 10 or lower, we're going to consider that a slow reaction. Again, fast and slow is a function of why we care about it is a function of what we're going to do with the chemical reaction. For stuff that we don't want to occur, right, we might want to slow it down. For things that we do want to occur, and we want them to occur fast, we might speed it up. And remember, K is a function of temperature. K is a function of temperature. Up until this point, we have not changed the temperature in our mathematics. So today, the mathematics are going to involve changing temperature. So when we talk about first order reactions, remember, first order reactions only depend on one reactant raised to the first power. We showed you in the last lecture how to determine that, right, looking at particular data. Now, we're going to look at what is known as the integrated rate law, but on your in-class worksheet, this is the first question that's asked. What is the equation, or what is the expression for a first order reaction? That would be rate equals Ka, and A being some arbitrary reactant. So in this case, they show you methyl isonitrile into acetonitrile, which is a conversion, not necessarily a decomposition, but this is a conversion reaction that involves one reactant raised to the first power. You know why? Because it rearranges pretty much with itself. It doesn't need another reactant. It doesn't need another molecule to do that rearrangement. Right? So this is a first order reaction. Now, we know this equation. Now, the math that's done here is pretty much calculus. I know all of us do not have that kind of background. For those of us that do have the math background, though, realize that all they've done here is substitute in a disappearance of A over time. Remember, that's why they show negative. Therefore, they rearrange this to equal that the rate is equal to both of these values, and then they rearrange this to show change in A over the concentration of A is equal to negative K delta T. If you integrate, and integration is a calculus function, the integration of A with respect to 1 over A gives you natural log. I'm not going to go through that. If you go take a look at some of my videos, I think I go through that integration. But it's not necessary for you to be able to do the calculus here. But this equation that you get at the very end of the integration of a first order reaction, this equation is on your reference material. It's underneath the kinetics portion of the reference material. That is what you're going to need to recognize, one, to be able to use. Notice that it follows the equation of a straight line, and we're going to do some plotting today, remembering that y equals mx plus b, where y is your y-axis variable, m is your slope, x is your x-axis variable, and b is your y-intercept. Okay? So this is y equals mx plus b, where we have a negative slope. So the plotting of data from a first order reaction, if it is in fact first order, should give you a straight line with a negative slope. And it should be linear. Now, what they show here is that conversion. We already have been told that it is first order. And if you look at pressure or concentration over time, remember we should see this kind of curved line, right? Because eventually it's going to flatten out. Remember, when we talked about average rates and instantaneous rates, we could go to this graph and do that via the tangent line. But let's say that we wanted to know different concentrations at different times, then we need the integrated rate law. We can't do that without the integrated rate law. We can only know average and instantaneous. We cannot know the exact rate at different times. We cannot know different concentrations at different times given a K value. So that's what this plotting does for us. If we took the natural log of the pressure for each of these data points and we plotted it against the same time x-axis, we get a linear line. There's going to be some problems and some Workout Wednesdays where I show you going into Excel or going into a calculator, and you can do this. We'll do this in the laboratory as well. Now, if we have this equation, it is again related to that rearranged equation. So The first question that asks you what is the integrated rate law for the first order, that's your answer right there. Yeah.
You said that the equation for the integrated law is the one with the natural log of A.
This one, correct. On the reference material, it's rearranged, but it's the exact same question. I mean, exact same equation. On the reference material, I don't think it gives it to you in y equals mx plus b, but it still gives it to you. It gives you ln of AT minus ln of A naught. Notice that this A here, when we see A, concentration A of T, this is concentration of A at time equal to T, whatever your time is in the problem. If they give you after 30 minutes, what is the concentration? That is time T. After 3 hours, what is the concentration? That is time T. A naught, and you'll see naught, which is little zero. You'll see naught all throughout the course. A naught is going to be concentration of A at time equals 0, or the start of the reaction. You might say, reaction was started 3 hours later, what's the concentration? That would be A naught. So if they give you, you started with 1 molar, what is the concentration after 3 hours? 1 molar would be A naught, A at time T will be AT. And we're going to utilize that here in a couple seconds when you talk about one of the worksheet problems. Okay, so if you were to have the data, let's say, for each of the concentrations and the given times, the plot of that, if you were to get the equation of a straight line associated with that, it will be negative K. Therefore, if I did not give you K already, then you could find K if you had concentration and time data, and vice versa. If you had K, then you can find any of the rest of it, right? So either you're going to be given one or the other. There are 3 variables in this. You have to be given at least 2 of them. There are 4 variables in this. You have to be given at least 3 of them at some point. Now, when we talk about the half-life of a particular reaction, it's essentially the time it takes to lose half. Very straightforward for the most part. And the half-life equation is given to you on this PowerPoint. It's not on the reference material, but I will give that to you. And the half-life equation is equal to T1/2 is equal to 6.693 over K. And this is for first order only. The half-lives are different for each order. We're talking about first now. We're going to talk about second order next. But first order half-life is only dependent upon the reaction constant. And it should make sense. Because if it is first order, then it means it only needs 1 molecule effectively for the reaction to occur. So it doesn't matter how many of those molecules are around. It matters the rate constant, which is a function of the nature of the reaction itself. So a bigger K, a shorter half-life. Should make sense. Bigger K, faster reaction, shorter time it takes to cut out half of it or to use up half of it. And when we talk about half-lives, and we're going to get to some half-life questions as well, we talk about half-life, the reason that it's applicable is because chemists, chemical engineers, they say, okay, how long is it going to take me to use up half? Because then that can make me figure out what I want to do with this reaction. How much do I need to start with so that it'll go for 2 weeks? How much do I need to start with so it'll go for 2 hours? So half-life is, from a practical usage standpoint. Plug and chug here, obviously, first order can be done with that equation. Now, quickly, so that we are kind of stay on track with first order, let's go to number 3, and then we'll come back and talk about 2. Because we haven't talked about gases yet. We'll talk about 2 when we get to 4. So number 3, I tell you that iodine decomposes at a temperature 625 Kelvin. So this would be an example of calculation involving a first order reaction. So I tell you that temperature is equal to 625 Kelvin. I tell you that it is a first order decomposition. How do we know that? Because the rate constant Rate constant tells us order. Even if I don't tell you what the order is, 271 seconds to the negative 1. 271 seconds to the negative 1. If I tell you nothing about the order, if you have K, you know the order. If you recognize the units. Units of K, seconds to the negative 1, means it's first order. So realize that every time I may not tell you that it's first order, you may need to be able to figure it out via data analysis, or you can look at the units of K. All right. I also then tell you that the starting concentration, or I2 naught is 0.05, and I want to know what remains after 3.29 minutes. So I2 naught is equal to 0.05. Remember, concentration is in molar, that's moles per liter, and my T is equal to 3.29. What did I say? Yes, 3.29 minutes. Okay, now I always like to write down all my numbers, look for any unit discrepancies. We see we have a unit discrepancy here. Seconds is what our K is in, time is in minutes, we need to convert that. So 3.29 minutes is converted into 197.4 seconds. Okay. Now, we have 1, 2, 3 variables. We're looking at the integrated rate law, and we know A naught, we know T, we know K. We are looking for the concentration at this time. Notice that I have given you ancillary information. 625 does not need to be used in the calculation of this, right? It doesn't need to be used in the calculation because right now we're still working at a constant temperature. Expectation is that we're working at constant temp. So if we rearrange this equation mathematically to solve for I2 at time t, which is what we're looking for, then we see that we have ln of I2 equal to negative K, 0.271 seconds to the negative 1, times T, 197.4 seconds, plus natural log of 0.05 mole. Now, one thing that's mathematically a little confusing is going to be units when we're dealing with natural logs, but generally speaking, natural logs are unitless. Natural logs are unitless, but when you utilize the inverse function of natural log, right, it will give you units back, right? So in this case, once you do the math here, you end up with negative 56.49. So you get natural log of I2 is equal to negative 56.49. And this is technically unitless because we have seconds to the negative 1 seconds. They cancel, and then natural log gives you units away. But when we do the inverse function of natural log, which is e exponential, then we end up with e raised to the negative 56.49. And since we know we're solving for concentration, we have to regain our units of concentration. And once we plug that into the calculator, we see that we get a very small number, 2.9 times 10 to the negative 25 mole. So this is a straightforward question that asks us to plug in values to a equation, rearrange that equation, and solve for a variable of interest. In this case, is I at time t, and you can put that there if you want to.
Another question. So, instead of using natural log, you use e.
Because that's the way to get rid of natural log on both sides.
Okay.
Natural log is a function, so you have to use the inverse function to get rid of it. You can't divide by the natural log. You use e. So e raised, this raised to e raised to this gives you your variable. Yeah. Now, what does this value say? Now we're talking conceptually, right? Everybody, not only do you need to be able to do the math, but you need to be able to think about things conceptually. What does this concentration tell us about our reaction after 3 minutes? Remember, K is constant, but we don't know if it's happening faster or not. Actually, we know that it's probably happening a little slower, but what does it tell us about our reaction after 3 minutes? What does this number say to us?
The amount of iodine is lower than when the initial.
Okay, that's one, right? So that is expected though. You don't need this number to tell me that the amount of iodine should be lower, right? I'm telling you that a reaction is occurring, so it has to be lower. But what does this say about the reaction? What is this? What do we know about this number? What is this number? This number is extremely small. This is extremely small. So what this means is that our reaction is pretty much over with. The rate that this is happening with a concentration this low is going to be really low rate. So what this means is after 3 minutes, whatever decomposition reaction is occurring on my question is done. Because this is times 10 to the negative 25. There's very little, if any, iodine left, right? So what this is saying is that if we looked at different parts of the plot, right? If we looked at the plot of concentration over time, we're way down here. Okay? And if we looked at the plot of this, we're way down here on the straight line. So that's what I'm saying. Conceptually, understand that this, being able to just spit out this number mathematically, those of you all with math skills are going to find the majority of this course, oh, this is straightforward, this is easy, right? It's when I start to ask the conceptual questions that go along with it is where some people are going to be there, some people are not. So what I'm trying to show you is that this isn't just a plug and chug math course, but you also need to be able to describe, okay, what does this number tell us about our reaction at 3 minutes? It tells us the reaction is pretty much over with. Any questions? So this is solving for one variable in a first order integrated rate law. Notice that we have talked nothing about rate in this equation because there is no rate here. It's just concentration and time. But we're not looking at concentration over time anymore. We're looking at those variables separately. All right, so expect to be able to solve for any given variable in that equation using that equation. And then there's going to be, we don't have the time in the assessment to really do it where you kind of plot your own data, but we'll do that in the lab, and we'll do that, you know, as some activities when we get to the lab. So now let's talk about second order rate laws. So second order, this goes back to question number one. What does the rate expression look like for second order? It looks like this. Reactant raised to the second power. Now, it also could look like A times B, right? We talked about that. But for simplification purposes, second order rate law, especially an integrated rate law, if we got into A and B, it's beyond the scope of this class. So the kinetics here, we're going to only be concerned with single reactant raised to the second power. And that should be the answer to that part 2 of number 2. So if you do the algebra manipulation and then the integration and calculus, you end up with this equation, which is also on your reference material. It's also given in y equals mx plus b. Notice they have these flipped around. I don't know why, but either way, these two are interchangeable because it's a plus. So we're dealing with 1 over concentration of A at time is equal to KT plus 1 over concentration of A at the start. Y equals mx plus b. Very similar, only difference here is we're not dealing with natural log anymore, right? We're dealing with 1 over. We should expect this to be a positively sloped linear line, positively sloped. And that's what we see here for a decomposition of NO2. So NO2 decomposes to form nitrogen monoxide and oxygen, and it involves 2 NO2 molecules. We need both, okay? So because of that, it is second order, and we see that the first order graph, if we graph natural log against time, we see that we have a graph that is curved. That tells us that we are not dealing with first order. So to then go a step further and look at 1 over, now we look at the data and we see a positive correlation. We're going to do an activity today, if we got the time, where you're going to graph your own, because everybody needs practice plotting and graphing, because unfortunately we've done a poor job of getting people prepared for that. Because a lot of you can't even use Excel. Well, you at least got to be able to do it by hand if push came to shove. All right, so notice that we have the equation here. Remember, stoichiometry does not dictate order. You must look at data to do that. So the half-life of a second order is going to be given here, which is T 1/2 is equal to negative 1 over K A naught. And they've given that to you here. I don't know if that negative is supposed to be. Let me double check that. I think that might be an error in the PowerPoint. Because K is not negative, concentration is not negative. I think that's an error. This shouldn't be negative. Sorry about that. That's an error in the PowerPoint. You can't have a negative time or a negative K or negative concentration. So here's the half-life. You'll be given these two if you're asked about either of those. Notice that they showed you the calculation to be able to get this expression. I'm not going to ask you to go through all of that after the integrated rate law is derived. Okay, so number 4. We're going to talk about second order, but we're also going to talk about gases and the pressure of gases. So if we remember from ideal gas law in Chem 1, that PV equals nRT. If we assume ideality on the gases that we're dealing with, and generally we do to simplify things, then we should realize that all of these units here, we should recognize pressure, volume. Pressure is usually in atmospheres, volume is usually in liters, N is in moles, R is in liter atmosphere per Kelvin mole, and T is in Kelvin. Up until this point, we haven't talked much about pressures, but when we're dealing with gases as a reactant, it is much easier and much more effective to use pressure instead of concentration, right? Because pressure is more easily measured in a laboratory setting. So pressure is equal to nRT over V. We've done this rearrangement a million times. We've seen this in a problem in the gas law chapter. But what we don't really recognize here is that concentration is actually a part of this, because N over V is equal to the concentration of whatever we're dealing with. Which means that concentration of NO2 is directly proportional to the pressure. So NO2, in this case, they use NO2 as an example. I'm using NO2 in my example, but pressure is equal to the concentration times RT. If the gas constant is a constant and the temperature is not changing, then these are directly proportional, right? They are equal, as long as we're not changing temperature. So what does that mean for this equation? Well, if we need to use concentration in this equation, then we have the ability to do that by rearrangement, and then we see that P over RT is equal to concentration. And if we look at the units here, we'll see that they will end up in moles per liter because of R. Now, let's look at our question. Our question asks us to determine T, what amount of reaction time would have to pass for a change in pressure of a gaseous reactant. So we're still dealing with the second order reaction, but we've been given pressure, okay? So the pressure, P naught, they give us as what, 100? The starting pressure, 877 and then 215. So P naught is 877 torr. and P at time is 215 torr. We've been given a K. We know it's second order because of the K, and the K value here is 0.543. And we want to know T. So we're solving for a variable, in this case it's T. Now, our equation involves concentration, but we have pressure. We can manipulate that equation to get concentration by inserting P over RT into our equation. So you're going to see me, generally speaking, manipulate the equation first and then plug in values. The reason for that is because you're rewriting a bunch more numbers over and over again. So I'm going to solve this for T. To solve this for T, you end up getting T is equal to 1 over concentration of A at time T, and I'm going to use NO2 just to be consistent, minus 1 over NO2 at the start, all over K. Notice I'm using parentheses because in the calculator, order of operations is going to be the issue that most of you all are going to run into. You're going to have the math set up right, you're going to have it structured right, and then you're going to input it without the right amount of parentheses. So all I did here, subtract A naught to this side, or subtract NO2 naught, then I divide it by K. That leaves me with T. From here, all we have to do is plug in our values, making sure that our units cancel. This is where the torr comes into play, because the gas constant that you have on your reference material does not take into account the gas constant for torr. So I'm going to give that to you again. Constants that you are not solving for, I will give you, and it should be 62.364. Liter torr over Kelvin mole. All right, so now if we were to insert all our values, we end up with 1 over 215 torr all over 62.364 liter torr Kelvin mole minus 1 over 877 torr all over, excuse me, I'm missing temperature here. Temperature was given to us to be 420. Yeah, sorry, I didn't put the last variable, temperature. Now, the only reason we need temperature in this one is because we're showing this relationship, right? Otherwise, we don't use temperature. So this should be times 420 Kelvin minus 1 over 877 torr all over 62.364 liter torr Kelvin mole times 420 Kelvin. And this is all over 0.543. Molar to -1, seconds to -1. Now, once you do the math, you'll see that seconds to the -1 is the only thing that's left, because torr goes away. And because this is concentration, you end up getting moles per liter. Kelvin goes away because of the multiplication, and if you did all the units, you would see that this ends up coming out as a function of time. T is then equal to, once you plug this in to the calculator, you get 224 seconds, roughly. Which tells us that it takes about, what, 4 minutes-ish? Close to 4 minutes to decrease the pressure by that amount, or to decrease the concentration, because they are directly proportional. So this is solving for T, but this is a situation where you have a gas and you have the concentration of a gas given to you indirectly, if you will, as pressure. If this was just concentration like the last problem, you would just plug those in. Any questions? Let's handle these now. You got questions? Ask. Yep. All I did was plug in P over RT for both of these. Mind you, I guess this is a little misleading. There you go. Sorry. RT, T should be on the bottom of that fraction. Now, if you're somebody who likes to keep track of your math differently than me, that's fine. I don't care. Some people like to just go ahead and do each one of these calculations and then plug the values in and then recalculate it. By all means. I tend to just try to do it in one shot to save time. But this would be solving for T for a second order reaction. I just threw in a little, a little pressure concentration relationship in there because they talk a lot about gases and how gases are used. Any questions up until this point on solving equations with integrated rate laws first, second order before we move on? Okay. So there is another type of reaction. They're not as common, if you will, but there are some reactions that are considered zero order, which means that it doesn't depend upon any reactants. It only depends upon the temperature because the rate is exactly equal to the rate constant. And what do we say affects the rate constant? Temperature. So it's independent of the concentration of reactant. So if we plotted them linearly, we end up with this integrated rate law. Generally speaking, I don't ask too many questions about zero order because in the grand scheme of things, zero order are not that common. They're not really utilized that much, but they do exist. So we already talked about all of the factors that affect the reaction rate. Now we need to kind of talk a little bit more about orientation and energy. So up until this point, we talked about temperature, increase of speed, increase of interaction. We've already talked about increase of speed and increase of interactions, increases the number of collisions of our molecules and atoms. But we haven't so much talked about the orientation and the overall energy needed for reaction to take place. And we're going to talk about that next. But first, let's talk a little bit about this activity that I have on the back of this front sheet. So question 6 is a great example and hopefully can build some skills for you all that are not just chemistry skills, but a little bit of math skills and a little bit of can you properly plot a graph. So I'm going to go grab you all some rulers real quick. That way it'll help you out. But I have given you that we have a reaction that involves a reactant reacting with itself to create a product, C10H12. I'm telling you that you have a 0.05 molar solution and we monitored it over time and the data is shown below. So here's an example where I give you the data and you have to determine the order of the reaction based upon graphical analysis. So utilizing the graph paper, answer the following questions. What is the order of the reaction? And then what is the value of the rate constant? So determination of the order of reaction can only be done by doing what? Specifically, what would you do if I gave you this question? Plot what?
The time versus the concentration.
What is time versus concentration going to look like for every single reaction? It doesn't matter what reaction, if you plot concentration versus time, it's always going to look like that. Does that give us any information about order? No. So, what must you plot? Two other options. Let's plot y-axis as what values? that's already there. The other two options to determine the order of a reaction involve graphs that are either natural log of the concentration or 1 over the concentration. Hence why I gave you two boxes there so that you can convert those values via calculator. It's the only way to be able to determine order. This doesn't tell you. One of these will. But you have to convert the values of concentration using your calculator. So go ahead and do that. Fill in the table. And I'm going to grab some rulers so that you can then make you a graph. Make sure that you know how to use your calculator.
So, the way, I don't want to look at it that way because it's a little bit and it's supposed to be and it's much easier to look at it as a equation. So I would use it as
A is 0.
no, I'm going with this one so it's a reference. See how it's much nicer because then when that T is here, A is here. So that means it's the same thing, it's just put it
Okay, if you've done your mathematic conversion properly, you might end up having a shortcut for you. Then you should have the table filled in, and you should be able to see values of the natural log, where they start, where they end, as well as, actually, let me print that one. You two can share that one. Yeah. You two can share, and then we got, you all can share one. I need some more, but we're gonna have to just share these because I didn't want to take all of them from the lab. So you should be able to fill in this table. And you should be able to then determine the best method of plotting this data. So just being able to fill in the table is one thing, but being able to plot it is differently. Excel will do this for you, right? If you have an Excel, but let's say I gave you this question on assessment test, you will need to be able to do this. So what are the values for the natural log of the concentration of C2H5? If you read them from top to bottom, what are they? Anyone?
We don't have K.
Okay. Maybe we're not clear. All I'm asking you to do is to take 0.04 and take the natural log. So you don't need K. That's why we're plotting. We're solving for K.
I got a negative.
Okay, and you will. What is the value?
Negative 3.22.
Okay, what's the next one?
Negative 3.51.
Uh-huh.
Negative 3.73. Negative 3.91. And negative 4.05.
Okay, there we go. Now, what is the values for 1 over C2H5?
The first one is 25. The second one is 33.3. 41.6. 50. And 57.47.
All right. Okay, is everybody clear what I asked you to do? Fill in the table is asking you to just mathematically take the natural log of the value to the left and then take 1 over the value to the left. These are the y-axis variables on both of the plots that we need to make. All of these plots that you've seen up until this point are the same as what we're about to do. So we're about to make these 2 plots. Natural log and 1 over. But being able to make these 2 plots is not just this portion, it's also drawing a graph correctly, okay? Drawing a graph correctly. So, in the case of what we're dealing with, let me see if I can get the dot cam. Let's use that real quick. There we go. All right, let's zoom out. And I know you can barely see these lines. Okay, so if we were using a document camera and we needed to make 2 separate graphs, so we're going to use different areas of the graph to make 2 separate graphs, we know that the t values are going to be the same. So we're dealing with t from 0 to 200 in intervals of 5, right? And then we're dealing with values that go from negative 3.22 to negative 4.05. This is not a very large distance, right? So we can break our units down of our y-axis into small units. Let's break them down into 0.25. Actually, we can just break it down into 0.1, really. So if we started our value, we'll start our y-axis here. I'm going to just draw a y-axis. If we had to start at somewhere, let's start at negative 3.2. So let's start negative 3.2. And if we were able to go all the way to negative 4.1, this would be then negative 3.3, negative 3.4, negative 3.5, negative 3.6, and so on. 7, 0.8, 0.9, 0, 0.1. Notice since we're dealing with negative values, that's the reason why this is going down. And I know this is unfamiliar territory for a lot of y'all. That's why I end up doing this. Okay, why did I do it in 0.1s? Well, I can still fit it within the area of my graphing paper. It gives me decent level of accuracy and precision on where I place my data points. And it's line by line, it's not so confusing. Now, if we're dealing with time, that's our x-axis, so we can make an x-axis up here, and not to have to take up too much of our space, because we got to put a whole nother graph in here, we can break the time up evenly since it increases by 50 each time. So we got 1, 2, 3, 4, 5. Best thing to do here is to go ahead and make each of these 50, 100, 152. We can do 2 at a time. Let's just do that. So let's do 50, 100, 150, 200. Right? So we'll go by 25s effectively. All right? So that gives us notches on each of our x-axis. So now, with our data from natural log, we can plot this. So at 0, we're dealing with negative 3.22. So that's roughly about right here, right? At 50, 3.51, which is roughly about right here. One 100, negative 3.73. which is a little bit beyond that right here. Negative 3.91 is 150. And negative 4.05 is 200. Which is right at the halfway point. Okay? Now, if we take a look at this, if we really take a quick look, we see that it is somewhat linear, right? Somewhat. But if we take our ruler or some straight object, we see that it's actually not very linear, right? It's actually kind of curved, right? We can look at just, if we put it over the first three, we see that our other two dots are out of the way. Same here. So, best thing to do is to graph both, and that's what I expect you to do. So, the next plot involves the same number of values for the time, so we can go ahead and repeat that time value, right? 50, 100, 150, 200. But now we got to do some more thinking about, well, sorry, this is positive, so I'm not going to use that line. Let's set the time value down here because we're dealing with positive values. Sorry about that. So now we need to break down 1 over, and we see we go from 25 to about 60, right? We go from 25 to about 60. So, best thing to do here is we can go by 10. We can go by 10. 10, 20, 30, 40, 50, 60. Now, this graph is going to be a little tighter, but it's still a linear graph. It's still plotting, and we should still be able to see whether its linearity is better than the other. So, at 50, we're dealing with 25. Sorry, at 0, excuse me, we're dealing with 25. So that goes there. At 50, we're dealing with 33.3, which is roughly about here. Again, everybody's is going to be different. You don't have to make your graph with these breakdowns. You could have made it by 2. You could use up more space. It's up to you. 100 is going to be 41.6. which is going to be really close to that 40 line. 150 is going to be right on 50. And 200 is going to be 57.47, which is really close to that 60. Okay? Now, if we take any straight edge, we should see that the actual linearity of this is a little bit better. And you're not going to be able to see that because of the glare. But see, the linearity here is very good, right? We're looking at a straight edge, we see good linearity. If we do the same thing over here, we do not see that level of linearity, right? Hopefully you all see that. They're very close, but you should be able to recognize, looking at two plots or plotting the data yourself, which one. Now, if we put the proper units on each of these, which we should, this should be ln of C5H6. And this should be 1 over concentration of C5H6. After we plot this data and we analyze the data, the answer to question A is going to be what? This is a second order reaction because the plot of 1 over is linear. That's the reason why. So not only do you need to know the answer, you need to know the reason, because I may ask you the reason. Say that again. The order of the reaction is second order because the plot of 1 over the concentration of the reactant as a function of time is linear. The LN plot is nonlinear. Therefore, it cannot be first order. All right, now we get into the nitty-gritty of where people that remember our elementary, I guess this is middle school, high school math. To determine K, we must realize that if 1 over concentration is the y-axis and T is the x-axis, we must remember that 1 over C5H6 is equal to KT plus 1 over C5H6 initial which means that the slope of our line is equal to K, because this is Y equals mx plus b. Therefore, to solve for the slope, you can do it a couple different ways. You can do it from the graph, or you can do it from the data you've collected. However you want to do it. Both ways should give you something reasonable. Now, for those that don't remember how to do it from a graph, the best thing to do is to take a data point that is an exact position. So the best thing to do would be take the data point at x equals 150. So take this data point and relate that to a point on your straight line. Let me see. If you drew a straight line here with your data, as best you can, I usually try to draw a dotted line. If there's any part of that dotted line that looks like it comes in contact with a crossing portion, which is kind of like right here, then I would actually take the rise over run at this point and slope is equal to rise over run. So this is basic graphing 101, and I just have to teach this because there's very few people who kind of remember or know this. So rise over run in this case will be 20 over 25 to 150, 125. So we got 20 over 125, and if we plug that in the calculator, we end up getting 0.16. So 0.16, and that would be molar to -1, seconds to the -1. Rise is equal to the units of Y, run is equal to the units of T. So there is our K. Now, you need to know that maybe this is 1 over T. I might, either way, your graph is still going to be the same. I might have, it should maybe be 1 over T. But you can still, let me see, let me go back. Wait this thing up. All right. No, it's still, as a function of S, you still could be able to calculate K via the slope here using this linear relationship, and you can also calculate this using the data. So if, let's say if you went back and plugged in this as at time 0 and this as time that, you could determine K that way as well. But you would have to know that it was second order and then utilize that equation. But the value of the rate constant is 0.16. 0.16 mole to -1, seconds to -1. And you can write that down. But you could also plug in the values into your equation and you should get something pretty close. Let's see. If you used that equation, you would end up with, just to verify that, you're going to end up with K equal to 1 over C2H5 at time t minus 1 over C2H5 not divided by time. So 1 divided by, let's just do these two. 33.3 minus 1 divided by 25 divided by, oh, excuse me. These values are already done. Sorry, don't divide them again. 25 hold on. Did I rearrange this incorrectly? I'm sorry. Real quick. I'm trying to show you two things. I didn't plan on doing this. Okay. Yeah. K equals. Did somebody give me the data? Time 50 should be 0.16, but it gives me a negative. I'm trying to figure out why it's negative, but this is what you get when you calculate this way. It should be a positive. There may be an error in this. It looks like they did something where they're missing a negative. If we look at the equation over here, yeah, this PowerPoint is wrong. No, is it? No. It should be at time minus equals KT. You can't have a negative K. I don't know why it's listed here, but this is your slope of the equation. It should be 0.16. And you can get that in a multitude of different ways. Let me verify. Let me think about for a second. We'll move on. Think about why that should be negative, because at 0 should be a bigger number.
Small. It's 25.
Oh, I rearranged. I put it in wrong then. Yeah, this should be 33.
No, 25.
This should be 30. Yeah, and this should be 33. Yeah, I put them in backwards, I guess. 33.3 should be minus 25. Yeah, so it should be positive 8.3. Sorry about that. I got those rearranged. So as easily as I can be in a hurry, you can be in a hurry in an assessment situation and make that mistake, but this should be molar per second, and you can verify both ways. But I just like to show that graphic example. I know it takes up a decent little chunk of time, but the graphic example is important because a lot of people are not familiar with graphing. That's the way you can determine the order if you knew the data. All right. Lastly, we're going to be talking about activation energy and the kinetics. So again, up until this point, we talked about constant temperature. Now we're going to talk about what happens when we can change temperature. All right. Generally speaking, right, we've already said K increases with T. If T increases and K increases, then we expect rate to increase. But since the rate constant K is temperature dependent, it also changes. And they claim approximately across a bunch of different reactions that you can double the rate constant with 10 degrees Celsius increase, which means that just heating it up just by a little bit can double the rate constant, which can double your speed of the reaction. And the reason for that comes back to the idea and the concept of the collision model. And we talked about kinetic molecular theory in General Chemistry 1. Molecules must come in contact with each other to have a reaction. If we have more contact, more reactions occur. If we have more molecules to be able to come in contact, then the rate should increase. These are basic conceptual stuff that you're definitely going to have to know, because you're going to get a question on the quiz next week and on the assessment test that talks about the theoretical nature of reactions and kinetics. So you got to know that stuff. And in a chemical reaction, you have to break bonds and form bonds, and you can only have the breaking and forming of those bonds if they collide. Now, one step further, we should also be comfortable with understanding that bonds are electrons. Electrons are in a cloud, if you will, and those clouds surround the area around the atoms and between them. So those clouds have to interact to some degree to get these bonds to break and form. So that's kind of on an atomic scale. So one thing that's very important, though, is that just because they can collide does not mean that products will form. Orientation matters. Same concept with anything else, right? Two cars that hit one another, depending on the orientation, may depend on the damage done to the car, right? Head-on versus T-bone, that differs in what you expect to happen to the vehicle, right? Same concept applies with molecules. If you need this orientation for the reaction to occur, if you need this, then molecules that collide in that orientation do not produce. No reaction. So, if you think about molecules in solution or gas, we have Brownian motion, right? We have motion that is completely randomized, and we have motion that can be in any one of these orientations in 3 dimensions, which means that there's only going to be a fraction of molecules that have the correct speed collide in the correct orientation. So, the more difficult or the more specific orientation that's needed, we should expect the slower a reaction that occurs. And that's why protein interactions, when we talk about those that are interested in biochemistry and protein and enzyme, you need the protein and the enzyme to interact at a specific orientation, or else the chemical reaction doesn't occur, right? And you have to break the bonds. So, aligning of the molecules and the collision can actually occur if you've got the proper orientation. And they give you a good visualization there that you can see in the PowerPoint and the text. Now, the one thing that we haven't talked about, and the one thing that we've been assuming up until this point, is that all of the reactions that occur, the molecules are reaching what we call activation energy. Essentially, they are reaching the energy barrier that is needed. They use a golf as a great example. Putting the ball, if you don't get the ball over the hill, the ball is just going to come back to you. But what do you have to do to the ball to get it over the hill? You have to impart some kind of force to it. That force gives the ball some kind of kinetic energy, and that kinetic energy, if it is enough, will get you over the hump. That hump in chemistry is known as activation energy, and we should be familiar and have seen the diagram of potential energy, or enthalpy. You also see this listed as delta H, where the difference in final and initial, right, is delta H. So if this is the beginning of the reaction, and this is time, and this is potential energy, if we can get over the hump and we create, this is reactants, and we have products, the other important variable here is going to be this value. And this value is what we call activation energy, or you'll see that listed as EA. So, the change in enthalpy, the change in potential energy goes over the hump. At the top of the hump, we have what is known as the transition state. Not so important for this course, but you will see that in the vocabulary, you'll see that in kind of the conceptual stuff. You need a transition state, which is kind of a very, it's a short-lived state of the molecule before it goes to the products, but it is no longer just the reactants. But to get to the transition state, to allow those bonds to break or form, you have to reach the top of the hill. And what they're showing you here is, I don't know what I did with them. What they're showing you here is the same type of graph using the molecule from earlier. So we see it has to achieve transition state, activated complex, and then once it becomes the product, we have a difference in energy. They are just using delta E. A lot of times we're going to see that as heat released or heat absorbed, and that is enthalpy, remember? And enthalpy is endo or exothermic. So in this case, we have a negative delta H. Therefore, remember, negative delta H equals exothermic. So heat is released in this situation. This is all Chem 1 for the most part. Now, the reverse of this reaction, which also can occur, and we're going to talk about reversible reactions a little bit later in the semester. The reverse can occur, and it will be endothermic, because we got to put more energy in to get to the activated state, right? The reverse of this has a higher hill. The key here is activation energy and what it means. So definition was given to you as a question. And how does it relate to K? So activation energy and temperature has a relationship that is based upon this equation, which essentially tells us that activation energy and temperature are not really, they don't have a huge differentiation over temperature. Why? Because what they saw is that the slope is constant for a particular reaction. So the relationship between activation energy and temperature is not, the relationship is not directly related to one another. Activation energy is more so related to the nature of whatever chemical reaction we're dealing with. So by definition, they list it as the minimum energy needed for the reaction to take place. Activation energy, and it should, hopefully it makes sense, right? Activation energy, whether the molecule is A plus B, whether it's A plus B at 100 Celsius or A plus B at 1,000 Celsius, this is, from a conceptual standpoint, this would be a great question to ask yourself. What do we know for a fact is different about both of these? Like, what do we know is going to be occurring differently in each of these scenarios? We got a reaction at 100 and 1,000. What do we know for a fact is occurring differently? What is going on different in both of these?
The time it takes for something.
Okay, the time it takes for what?
For stuff to react.
No. The time it takes for A and B to collide should be lower at a higher temperature. Why? More collisions. Frequency of collisions. We know that, okay? What else do we know? This goes back to Jenkins 1, kinetic molecular theory. Frequency, what else is happening at a higher temperature? Collisions have what?
They give off. They give off.
No. Simpler than that. They're occurring with greater energy. Higher temperature, higher kinetic energy. So they are hitting each other with more energy. Those are two things that you know for a fact are occurring. More collisions, hitting each other with higher energy. But the activation energy that it takes to get across this barrier is a function of the nature of the reactants, meaning what kind of chemicals we're dealing with, and how many different orientations, if you will allow you to get to C. So temperature does not affect orientation, but it does affect how many more collisions are happening, which can then affect how many more times that orientation will occur.
That makes sense.
Of course. It's just, and you think about people, right? You might, you go out, hang out with your buddies, you might hit it off with only certain kind of folks. But if the place got way more people in there, that doesn't necessarily mean that you're going to hit it off with anybody, but it does mean that you have a higher likelihood, but it is internal why you like someone, right? That is not something that the different locations are going to change, right? You could go to 3 different places, but you still have something you're looking for, right? You want them to be 6 feet in shape. That doesn't change just because you go to a different place, right? Which is what the temperature is. But if you go to, NBA party, everybody's going to be 6 feet. So that's the nature of the environment, the nature of the chemicals, right? But here, it is a function of temperature does not dictate activation energy. Activation energy, for the most part, we see is consistent over the range of temperatures that we normally deal with. But because of that, what I just explained is shown here, right? The minimum for the reaction is listed here, and any molecules that are beyond that have a likelihood of reacting. Notice that at a higher temperature, the distribution, which is statistical thermodynamics really, notice we have a lot more, larger fraction of molecules that can react. But activation energy does not shift as a function of shifting temperature. So their relationship is not directly related. Now, these three equations here are going to be equations that you are given. I don't think that they're on the reference material, but I will put them on any of the assessments, tests, quizzes. But you need to know how to use them. So, the next question says, determine activation energy of the reaction in question 4. So we're going to go back to 4, and 4 was the decomposition at a second order. Notice, Arrhenius equation, which is the equation listed here, can be manipulated in 3 different ways. You just kind of need to know which one to use. I'm not asking you to do the math to manipulate. It does not depend on order. This equation can be used for any order because K1 and K2 are going to end up getting canceled out, right? So the units, and notice that you have no, this collision factor, let me say, which is A. This collision factor is a constant. That value is a function of how many molecules are colliding with the proper orientation. That's what that is, really. It's collision factor. It has to do with orientation. That is a constant. It is a function of the type of reaction we're dealing with. So you have to be given that, or you could potentially solve for that if need be. So I asked you about 4, which is a second order decomposition, and I asked you to determine the activation energy. So I'm asking you to solve for EA, and you can solve for EA using any one of these two, if you would like to. Simplest way is going to be to use the second one, which means that solving for EA gives us activation energy is equal to natural log of K minus natural log of A divided by multiplied by negative RT. So all I did was rearrange this equation here. One thing that you'll know about natural logs, not that it is necessarily important, but any of the natural logs, if you see one natural log subtracted by another natural log, that is the same as saying natural log of K over A times negative RT. Same thing, but it's up to you how you want to input it. So that gives us a value in joules, because the R value we use when we're dealing with Arrhenius, very important, R value we use with Arrhenius is the one that involves joules. So we always use 8.31 joules per Kelvin mole for Arrhenius. We do not use liter atmospheres because we're not dealing with gas pressure, we're dealing with energy here. So we have to use 8.31. That's also given on the reference material. You have that. And for this particular problem, I think it ends up being 90-something thousand, 93,122. 93,122 joules per mole. Remember, any natural log takes away units. So all of our units here are just R times T, which give us joule per mole, because K is canceled. I'm just not rewriting this out. If you plug all those in, you should verify that value. So all we did was plug in the numbers given to us in the problem, number 4, which is temperature, and K. This problem gave us A, and R is a constant, and I've asked you to just solve for activation here. Next, I ask you then to determine the rate constant at a different temperature, right? So the rate constant at a different temperature is when we need to use an equation that gives us an option for two temps, which is going to be this third equation. So we want to know rate constant at a different temperature. That's going to involve using this equation and manipulating this equation for another K. The best thing to do here, and I'm going to do the manipulation here just for folks. I don't like continually doing this, but we have it in Workout Wednesday where you can see some of that as well. Okay. If you think mathematically, you got to think one step ahead, right? You got to think what's going to give me the least amount of mathematical manipulation to get me what I want. Best thing to do in this case is solve for K1, meaning that the T1 needs to be your 1,000. Okay? Hopefully people understand that. You've been given T1, I'm going to use as 1,000 K. We're looking for K1. We've been given T2 and K2. Technically, it doesn't matter which one. This is not a final and initial situation, right? This is an equation that gives us a value at two different temperatures. So, because number 4, we already know that we're dealing with 420 and 0.543. So we're dealing with 420K and 0.543 molar second. All right, so we're looking for K1. Why did I pick K1? Because K1 is already in the numerator. It saves us some time. Honestly, it just saves us some time. So, to get rid of the natural log, we use exponent to get rid of it, which gives us K1 over K2 is equal to E raised to all of this. Okay? EA over R times 1 over T2 minus 1 over T1 in parentheses, and then we need to multiply that by K2, so we're dealing with K1 equals K2 times E raised to the EA over R 1 over T2 minus 1 over T1. Again, the math heads, this should be easy peasy. The people who are not comfortable with the math, this whole chapter and pretty much everything after this is bad. I mean, this is just a math heavy course. All right, we have all of these values. We have the activation energy. We just solved for it. We have R, we have T2, T1. So K2 is 0.543 molar per second -1. And then this is multiplied by E raised to the activation energy can be left in joules if your R is left in joules. So 93122 joule mole to -1 all over 8.31 joule Kelvin -1 mole -1 times 1 over T2 in this case is 420 minus 1 over T1 is 1,000. These are both in Kelvin. And if you plug this into the calculator correctly, which is going to be important, parentheses, or do it one by one, step by step, whatever makes you comfortable.
I have a question.
Yep.
So, I understood the concept of how you got it, but you lost me on to which equation we ended up using in the end. Because you wrote one on the board, and I wrote it down, and then you used another one. So you used ln K1 over K2, right? And then you manipulated it into E, and you ended up getting K1, right? Or
Yeah.
yeah.
That's why I showed you each step.
The,
Exponent gets rid of ln, which means you have to raise this to the exponent.
yeah.
Multiply both sides by K2 to get K1 alone.
That's
then K1, manipulate it to give us the answer in this particular case. And the answer ends up being what looks like 2.85 times 10 to the 6. And this is going to be same units because it's second order. Notice, what do we notice about the size of this value? It's large, right? It's considered, it's bigger than this value. So we see this almost 600-degree difference should increase and make our K value larger. Makes sense, right? Makes sense. Now, the reason I showed you how to do it this way is because you may not always get the collision factor, right? In a problem where you don't get the collision factor, this is going to be the only way to do it. In the problem that I just gave you, because I gave you the collision factor, you could also do this just using the initial equation. So a little simpler, but you may not be given A. Then what do? You can't solve for it, right? So in this case, I gave you A. You can use that one. In a lot of questions you'll see in some of the homework text, they may not give you A. They may just give you the activation energy and 2 different temperatures and 1 K. Then you have to use that because this is going to do you no good. So you could have used that one if you want to. You get the same value. Activation, that A, since it's a constant, is implied within this equation once you do the manipulation. They don't really have to show you that math involved. So that is, any questions up until this point? We've covered pretty much all the way to activation energy. We're going to talk a little bit about the mechanism stuff, which is also already online. But any clarifications needed, we have a little bit of time cushion here. Any clarifications needed on any of the problems, any further examples needed on any of the conceptual or computational problems?
Oh, it's just the conceptual part of it, where it was, I think it was on 6.
Okay.
Where you were saying that that seeing which one the concentration, the final concentration, how it relates to the initial.
Okay, are we talking about a particular plot? Are we talking about, you're talking about when I was determining the slope of the plot?
No, when it was when we were finding out the rate constant.
Okay, yeah, determining the slope.
Yeah.
Okay, so I determined the slope. You can determine the slope one of 2 ways. You can determine the slope, and I don't have that data still written down. But if what is the data for 1 over, and I'll clear that up, C2H5, we can clear that up right here. So T equals 0, 50, 100, 150, 200.
It's 25,
33.3.
41.6, 50, and then 57.4.
Okay, all right. If you had been given this equation, which is 1 over C2H5 at time t is equal to KT plus 1 over C2H5 at time 0, it doesn't matter which 2 data points you use, you just have to make sure that you plug them into the right location. Now, when I say right location, you should understand that if you pick 2, let's say you pick at time 0, then this value here is this entire component, right? So this is 1 over C2H5 at 0.
Okay.
So once you manipulate this equation and you get 1 over C2H5 at time t minus 1 over C2H5 at 0 is equal to K, and this is all over T, then at time T is whichever one of these other ones you pick. It's up to you. I picked 33.3, but you can pick this last one. Let's say we pick the last one. Then this one, because this is at some time T, then therefore this is 1 over C2H5 at that time T. This should be larger because concentration is decreasing. So 1 over a smaller number should give you a larger number. So now this goes into this goes into that, and we should end up with 57.4 molar to the -1 minus 25 molar to the -1 all over 200. Why do we pick 200? Because this is T. Therefore, this is equal to K, and this should give you 0.16. All I did was I had a flip. I just flipped them around. That's fine. You still get the same magnitude. The difference is just going to be negative. So I had T as 0, either way. Now, you could, even if you did mess up and you got a negative number, you know that K can't be negative. So you still have the right answer. You just take the negative one. Cleared up? Any questions?
Yep.
Okay. Mr. Kane, you had a question?
Oh, yeah, I guess something. It's about number 2 and 7.
2 and 7? Okay. You said question number 2 about the relationship of pressure? Okay.
It's the relationship between concentration of gases and pressure of gases at a given temperature is length proportional.
Correct. It would be directly proportional. Directly.
Okay. Why?
Why? Because of the ideal gas law. We talked, I showed that in the notes earlier. What's up? I showed that in the notes earlier. PV equals nRT because pressure is then equal to NV over RT, and NV is equal to molarity. Moles over liters.
All right.
Yeah.
And number 7.
Mm-hmm.
2 variables that ultimately dictate whether a chemical reaction takes place.
It's going to be collision or orientation of molecules. I say collision orientation, either way. The orientation of the molecules itself and the activation energy.
All right, got it.
Mm-hmm. Any more questions? Then we'll talk a little bit about mechanism. But any clarification then? Okay, come on.
Okay, so on number 9.
This is this one?
Yeah.
Okay.
The one we just did. Before we did all of that, you got the 9.
Yeah, I solved for activation energy in the first part of the question.
Okay, and that was a different equation, right?
I utilized a different equation, right? I utilized the very first equation because I had all the information that I needed. I utilized K equals for the first one.
Okay. And then after you saw that, then you used what you got for the second equation, right? For the ln K1.
Okay, so let me this is where the math is getting people off track. All these first 2 equations that you see up there are the exact same.
Oh,
Only difference is that they did the mathematical manipulation. So I'm going to take this down. Okay, so maybe this will clear things up for folks. But again, a lot of it has to do with the math background. So if K is equal to A E raised to the negative EA over RT, all right. the way we solve for activation energy, in this case, is to take the natural log of both sides. Okay? Now, you can do that here, or you could manipulate first. One of the rules is if you take the natural log, right, of two things that are a product, if you take the natural log of this entire thing, okay, that equals the sum of the natural log of both, which means that you end up with natural log of A plus or minus natural log of EA, minus EA over RT. Let me say that. Natural log gets rid of exponent, okay? If you take the natural log then on the other side, we end up with ln of K. So that's where this equation comes from. All right? You can use either one of them to solve for what I asked you in the first one. But the problem is that you're going to have to go through these steps to get EA by itself. So what I did from here is manipulate this equation. I added EA to the other side. I added that whole thing to the other side. Is equal to ln of A minus ln of K. Then I multiply by RT. So you know EA equals ln of A minus ln of K, all multiplied by RT. But what I then said is you could also, if you know that the natural log of the product is a minus or a plus, it's actually a plus. The natural log of a product here, minus is a division. So this is the same as saying ln of A over K. It's just a bunch of different ways to represent the same thing. You just got to know your math and stick with one and stick with it.
Is there an easier way if you know calculus? Is there an easier way to go about this? Or
No. You don't. The only thing that's calculus based is the integration part. No. You have to know the integration of the original rate law equation. No, calculus. This is not calculus. This is algebra. All algebra. Exponents, whatever. Yeah. Well, just being able to manipulate things to one side or the other. That's all this is. But you gotta know your functions and the inverse of the function. Any more questions? Now will be the time to ask them. Remember, because we're a little behind, I want to try to. We're gonna quiz over Kinetics Wednesday, and that's gonna be the entire content. Then I'm gonna get those quizzes back to you before the exam. That will be on next Monday, right? So you'll have Kinetics homework due. Answer key to the Kinetics homework. You have the problem set to look at. But on Wednesday, because we do not have the lab and because I decided to make the Excel lab online, therefore that gives you a Wednesday to come in with any questions as it pertains to the problem set, any questions as it pertains to what you don't understand from either of the lectures. I'm going to give you back the quiz from today, and then we'll take the quiz for that. Now, any questions on this content that was covered today, and then real quick, we're going to talk about the last two questions, which are content that's over the mini lecture, and then integrated problem. Any more questions on first, second order integrated rate law, half-life? Did we do the half-life problem yet? No. No, we didn't. Okay, real quick. 5. Half-life. Since I gave you the equation, I asked you what is the half-life of a first order reaction? It's 0.110 seconds to the negative 1. So, K equals 0.110 seconds. We know this is first order based on the units. I told you it's first order in the problem. Therefore, we should use the first order rate, the first order half-life, which is 0.693 over 0.110 seconds to the negative 1, which is equal to seconds. How easy is that? Answer 6.3. So it takes 6.3 seconds to use up about half of your concentration.
I like that from
Yeah, expect to see one like that. The better question is then, if you had 100 grams, that's the second part of the question. If you had 100 grams how much do you have left when it goes through 6 half-lives? Okay. Bunch of different ways you can answer this, right, mathematically. However you want to answer it. You can use the integrated rate law, right? But how much will be left after 1 half-life? What is a half-life by definition? 1 half-life is the time, it's going to be 50. It's the time it takes to lose half. So that's 1 half-life. How much is going to be left after the second half-life?
25.
Ah,
Ooh. Yes, yes.
12.5, 6.25, 3.125. So that's 1 half-life, 2 half-life, 3 half-life, 4 half-life, 5 half-life. So what is this? 1.0625. Or if you're math savvy, which one of these days, I hope America gets better, then you can also put 100 over 2 raised to the 6th power, which is the same as dividing it by 2. All right. Now, half-life question as a standalone question? Probably not. Half-life question as a part of a larger first-order computational question? Most definitely. But here's the thing. This K value, you're going to have to solve for this K value in the earlier part of the problem when you're dealing with me, right? So it's going to be solve for K for this reaction, use K to find half-life, use K to find activation energy. So if you mess up in the front end, then the rest of it's no good, okay? Any questions before we talk about these mechanisms real quick? All right. So when we're talking mechanisms, you got to go watch the mini lecture, because I'm not going to lecture over that. But when we're talking molecularity of a particular elementary reaction, it has to be labeled as elementary. If it's not labeled as elementary, we cannot make this assumption. But for problems that involve mechanisms, it will tell you an elementary reaction was witnessed, blah, 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 blah. Uni, bi, and termolecular. That is the extent. Uni means 1, bi means 2, and means 3. It can either be bimolecular with the same 2 reactants, or bimolecular with 2 different, or termolecular with the same 3, so on and so forth. Now, for the example that I gave you in the molecularity and the reaction mechanism, I told you that mechanism has been proposed for 2 gas phase reactions with hydrogen and iodine chloride. So we're dealing with H2 plus ICl gives us HI plus HCl. All these are in the gas phase. And the second reaction that occurs, it happens in 2 steps, ICl and I2 plus HCl. All right, so if we call this first step and we call this second step, for each of these reactions, these are both bimolecular. Specifically, rate equaling K H2 ICl, and then this one is also bimolecular, and we got a rate equaling K HI ICl. Okay, hopefully we see that. That's just, we can only do this assumption. Remember, up until this point I've been telling you, you can't look at the stoichiometry, right? And the reason why I leave the mechanisms for the end is because in this situation you can use the stoichiometry, but you have to be told that it was elementary to begin with. So that is the differentiation you have to make. Now, the balanced equation for the overall reaction involves crossing out things that exist on both sides and adding up things that are on the same side. So hydrogen iodide gets crossed out and we're left with H2 plus 2ICl gives us I2 plus 2HCl. If we remember from Hess's law back in Gen Chem 1, adding up, getting rid of it, right? And the one thing that we talked about in Hess's law, we did not talk about in Hess's law that we talk about here, is anything that exists in the elementary reaction but does not exist in the overall reaction is considered an intermediate. So HI is an intermediate for this particular reaction. These are the two steps that give us these two products. So molecularity, bimolecular for both, identifying intermediates. HI has been identified as an intermediate. Now, they tell us that the first step is slow and the second step is fast. So what is the rate law that you should expect for this guy, right? Okay, this is where you kind of, if you haven't already watched the video, you're going to need to put a star beside this after I explain it and go back and rewatch or watch it for the first time. And it comes from a, you gotta be able to kind of wrap your head around this. If it takes a long time to create HI, which is the only guy that's a part of this that's over here, right? If it takes a while to create HI, the second step being fast essentially tells us that as soon as you make it, what's going to happen? It's going to get used up in this second reaction. So as soon as we make HI, it's going to get used up here. That tells us that the creation of these two products, which are the only products that we have in the overall reaction, the creation of these two products depend on the creation of the intermediate. And what dictates the speed of the creation of the intermediate? First step. First step, right? So if the first step dictates how much of this is made, and we know it's immediately going to be used up, then the first step dictates our overall rate law. So what we should expect the observed rate law to be is to be the rate law for the very first reaction. So we should expect the rate law observed to follow rate equals H2 ICl. And that is a very quick snapshot of mechanisms. I suggest you go watch the mini lecture where I go into that a little bit further in depth. I also have Workout Wednesdays where we solve problems where the reverse is occurring as well. And it may be more than one step, right? Maybe more than one step. But if IHI is getting used up as soon as it's being made, then the first step is what dictates how fast the reaction goes. Because we expect this to happen immediately. So this doesn't impact our time. This guy does, first step. So the overall reaction rate law should follow this. But again, this mechanism stuff is only good if you have been told that it is elementary reaction. If you have not been told that, you will not be asked any of these questions. You will be asked questions that we were talking about earlier today, right? Earlier today. Okay, lastly, and we can get on out of here. I like these integrative problems that they have because these integrative problems give us a little bit more insight into the kind of problems that I'm going to give you, because I like to try to wrap in multiple concepts into one question so I don't have to ask you a million questions. So I think it's 14.118, I think, or 7. Yeah, 14.118. Let's zoom in. Autofocus. All right. So they've shown you an aqueous reaction, right? So aqueous reaction, we expect that to be in some kind of liquid. This is kind of when you got all your stuff together, you should be able to solve some questions like this, because this involves everything, Gen Chem 1 and what we've learned. they've given us an activation energy and a frequency factor. So as soon as you see activation energy, frequency factor, immediately you should start thinking, okay, Arrhenius, we need to start looking at these equations. So if we got an activation, a frequency factor A, 2.1 10 to 11, M, -1, S, -1, and we have an activation energy, EA, equals 86.8 kilojoules mole to the -1. Now they're starting to ask us questions. Predict the rate constant for the reaction at 35 C. All right, so temperature is equal to 35 C, which should be equal to 308 Kelvin. Rate constant, if we've been given E, A, and frequency factor and temperature, we can use the basic equation, K, A, E raised to the negative E, A over RT. And we have everything we need, right? I'm not going to rewrite it. I'm just going to plug it. 2.1 E to the 11 times E raised to the negative 86.8 divided by 8.31 E to the negative 3. Remember, we got to change our units on R, times 308, because R is in Kelvin. Should be 3.93 E to the negative 4. And again, since we know that the rate constant is a function of the collision factor, then we should expect this to be second order, right? Because we see this frequency factor is the only thing left. Remember, we don't get units on exponents of natural laws. All right, now B, a little bit more nitty gritty, right? They ask us, given two solutions made up by dissolving these into solutions, and we have equal volume, and assume, well, in this case, they're saying assuming the reaction is first order. First order in each. Okay, it makes sense. It's first order in each reactant. What is the initial rate at 35 C? Okay, so now we're talking initial rate. When we talk initial rate, we're talking about rate laws that look like this. Why are we talking about rate laws that look like this? Well, they told us that it is first order in each. We have two reactants. Look at our equation. We should have each of those raised to the first power. So we should have C2H5I negative and OH minus. All right. Now, how do we get concentrations of these? Well, they gave us data to calculate concentration from a solution standpoint. So this goes back to our chapter 13, creation of solutions, right? Can you determine the molarity given volume and mass? And you should be able to. Concentration of OH minus is equal to the mass of KOH, 0.335 grams, all over the molar mass of KOH, which is 16 plus 1.01 plus 39.09, 56.11, and that's all divided by liters of solvent, which is going to be 2.250 liters. 0.335 divided by 56.11 divided by 0.25. So we got a molarity of 0.024 of OH minus. Hopefully this should be familiar. Concentration. All right. Now, if we're looking at C2H5I minus is equal to the mass of that 1.453 grams divided by 1 mole, and then we're dealing with 5.05 plus 24.02 plus iodine is 179, 126.9. So 155.97. All over 0.250 liters as well. So we're dealing with 1.453 divided by 155.97 divided by 0.25, and we have 0.037 molar. Okay? So this is integrated because they've asked you to do something that you should already know how to do. So when I ask you questions that involve concepts that are already understood or should be understood, don't find yourself in a position where you just know how to do a problem when they give you all of the variables, right? That is middle school, honestly. A math problem where they give you all the variables and solve for one is not college level work. I'm gonna just be honest with you. And you're not gonna see that, as you can clearly see from the quizzes. So we're dealing with this ratio, or not ratio, we're dealing with these two values. So from here, we want to know the initial rate at 35C. Well, we know K at 35. We know concentration at 30 that we haven't had. And they say if you use equal volume or mixed, which means that you can use a liter for each of these, which means that you can use these two values. So you have everything you need. Initial rate is equal to 3.93 times 10 to the negative 4 molar negative 1 second negative 1 times 0.024 molar times 0.037 molar. So rate, therefore, is equal to the product of these, 3.93 e to negative 4 times 0.024 times 0.037. 3.5 times 10 to the negative 7 molar per second. Part C tells us to determine which reagent is limiting, assuming that we have complete reaction. This goes back to basic stoichiometry, right? This is Gen Chem 1. Which one of these runs out first? Right, the OH runs out first, so OH minus is limiting because it is less. We're using equal volumes of both, so it is the one with the less concentration. And then D puts the cherry on top and says, assuming that the frequency factor and activation energy do not change as a function of temperature, calculate the rate constant at 50 degrees Celsius. You can use whichever equation you want to use, but they told you that activation energy and frequency factor don't change, so you can then use EA over RT, which then give you K equal to, all we've changed is T. All we've changed here is T. So 2.1 E to the 11 times E raised to the negative 86.8 divided by 8.31 E to the negative 3 times 50 Celsius is 323. should be 0.0019. And this should be m to negative 1, s to negative 1. And if you look at this and compare, you see that raising the temperature has given us a larger K value, which is what we should expect to see mathematically. So that is more of, I wouldn't say that I'm going to give a problem exactly like that, but that's more of a type of problem that you should be able to do, combining all of the concepts of all of what you've learned thus far in chemistry together to be able to solve all different parts of this, because we involve everything from basic Arrhenius equation to formation of a solution, determining concentration, going back to rate law, then going back and using determining limiting reagent using basic stoichiometry, and then Arrhenius equation again. The homework is thorough. I gave you the option in the homework to do the problem that you think that you are the most in need of. So the homework got all different kinds of problems, and it shows you examples for each type. It's a very good homework worksheet. It's very thorough. There is a workout Wednesday for almost each different type of content that we've covered today. I just actually changed one of them. I made a math error in the video, I realized going back. So I just changed one of them today. Again, on Wednesday, start off with a quiz, ask any questions you have, and then from there, bring your questions Wednesday. Bring your questions, whether it be problem set, whether it be homework, whether it be content. I'm not going to stand up there and go over all of this stuff again, right? So Wednesday is going to be your day to get stuff squared away for the following Monday. And it's lucky that you have this time, because normally we've already began laboratories by now. But just because I've given you the option to do the Excel spreadsheet online, that gives you the option to have this time to get really prepared for this first exam. You don't want to start off on the wrong foot, as they say. If there are no more questions, I'll see everybody on Wednesday. Make sure to put my reference materials back.
So I'm making a study group, so if anyone wants to put their phone number and name on it, they're already put the little number.
Yes, already on into it. It's called statistical.
That's for us to do first.
Do it on your own.
Is that what
No. The statistical analysis, so those people are asking questions about that. If you go on D2L and you see statistical analysis dry lab, that is what is expected of you. There is no pre-lab. There is a tutorial on how to use Excel. Realize that I'm a Mac user. So for those that are on PC, it's a little different, but not too far difference in making a standard curve, things of that nature. There's a simplified statistical analysis, which is the walkthrough, which is what you'll see me doing, is examples from the walkthrough. And then experiment 1 is going to be what I ask of you. I ask you to submit an Excel with all of these things done, which will be creation of a chart, creation of a graph, plotting of a straight line, determination of the slope of that straight line, etc. So all of that is expected of you to be done on your own. That is why we have Wednesday kind of free to do, kind of go over anything that anybody has questions with. My rulers, let's make a pile of those back on the back too. Again, reference materials, rulers.
We don't need to bring a card.
No, Wednesday is just going to be bring your questions. You're going to take the quiz and you're going to bring the questions and see if anybody has any clarifications needed, more practice, certain kind of answers, certain kind of questions, etc. The in-class worksheet is for you to keep. All of them.
Tomorrow I'm going to be here. Classes on Wednesday, so.
Say that one more time.
I mean,
I'll be available.
okay, we'll just let
Any questions that you have for the exam that'll be the following Monday. So anything that you don't understand from today, anything you don't understand from the previous lecture, anything you don't understand from 13 and 14. So any clarification questions you have about the chapters.
Just tell me what time. Then,
Okay, so I'm gonna be here tomorrow.
I work
Yeah, I was
tomorrow.
with,
And I gotta say,
he's a
my
biochemist
account.
from Ball State, he
Or
was on the
was
same
on
chapter
Wednesday.
as David did.
Okay.
And,
Did he be around like that?
yeah,
You married or something?
He ain't married, he's young for 2 years older than me, and he's in the Army and stuff too, so. So, yeah, so he lived out on this side as well, on my side of town. So he was helping me out, and that's what he was talking about, quantum or something, he was like calculus, like to make it simplified, but he was like, we went in depth.
Quantum mechanics?
Quantum mechanics.
Yeah, but that's not in it. You don't get that to upper level stuff.
Is there anything next?
Yeah,
He said
so
something
I'm
about
gonna be
question
here
four,
tomorrow,
homework too.
like
He was
all
saying
day.
something.
And then I'm also gonna be here on Thursday, Wednesday, Friday.
From the 13th
So
on?
whatever day works for anyone, really, just show up everyone.
We're here?
Yeah, what he said was
Um,
confusing, he
probably
said something about
like-
the grams or
Yeah,
something. He said
I'll
something
text you
about
my
tablets,
other
so
bag
I
real quick, I
did
forgot.
something.
No, see, you don't need that density. I gave you the density, but you don't need it. That's why I said, I was just putting it in perspective. Again, mole fraction doesn't have to worry about volume or density. Mole fraction is just mole.
Well, I'm gonna be here tomorrow, and I'm
Those
gonna
are,
be here
yeah,
a
you can
couple
sit
other
there.
days.
I saw those MCAT books, you know, I got them.
So whenever
I
you're
didn't,
free,
because he
just
said
let
something
me know.
that he's
because
trying to get ready
then-
to go medical something too. He
Oh,
went after he
okay.
got employed before he.
So I don't know how old or new the ones I have, but I got the ones for chemistry.
Yeah, this helped me a lot because they, you know, I'll look through the stuff, I'll read it, and do the MCAT stuff, and they give a lot of information. Like I knew about their intermediates and the reaction rates and stuff like that too.
I got you. Right, yeah. No, they cover almost a lot of the Jigsaw 2 stuff is going to be covered in those MCAT, but they don't go super in depth.
No.
But they're going to need you to know at least
They let the concepts, what you
yeah, the
see.
concept, the conceptual stuff.
Yeah.
Always. Always.
See, I could talk about concepts, but talk about plugging it in.